Okay, here we discuss, another topic in this chapter, describing data, numerical measures. Here we're going to talk about, of course, the relative positions of the mean, median, and mode. Here we're going to discuss three types of distribution concerning the relative positions of the mean, median, and mode. The first one is symmetric distribution. First one is symmetrical distribution. Of course, as you can see, this distribution has the same shape on either side of the center of the data, As you can see the data, this is the distribution, is symmetrical. Of course, you see the same shape, of course, on either side of the center of the distribution. This is kind of, histogram. It is normal or symmetrical. And of course, when we say symmetrical, it means the mean is equal to the median is equal to the mode, of course. And at the center, they are located at the center over here. They are located at the center of the data. And as you can see here, that the same shape is on either side of the center of the data. Okay, great. Now, of course, when we say about a symmetrical distribution, it means that the mean equal the median equal the mode. As you can see over here, if the mean is equal 10, then the median is 10 and the mode is 10. Now, this is one type of distribution, okay, concerning the relative position of the mean, median, and mode. Now, another type of distribution, it is non-symmetrical, which is here, it is positively skewed. It is non-symmetrical and skewed. So the second type of distribution is, positively skewed distribution. Of course, as you can see if you look at the graph of the positively skewed, it is, skewed to the right. Okay. Now, in this distribution, as you can see, the mean is the largest of the three measures. Is larger than the median, is larger than the mode. Why? Because the mean, the arithmetic mean, is more influenced, is influenced more than the median and the mode by a few extremely high values. And that should, tell us that the mean would not be, a good representative of the data. So the median and the mode in this case would be more representative of the data. Okay, when you have a non-symmetrical, positively skewed distribution, we will say that the median or the mode are better representative of the data than the mean, because the mean in that case is influenced by a few extremely high values, more than the median and the mode. Therefore, we cannot take the mean as a good representative of the data. In this case, we have to take the median or the mode. Now, the third type of distribution is still non-symmetrical, and it is negatively skewed. The graph, as you can see, it is skewed to the left. Negatively skewed, it's skewed to the left. As you can see, it's skewed to the left. This is negatively skewed. Okay. In this distribution, of course, as you can see, the mode is the largest. The mode is larger than the median, larger than the mean. So the mean is the smallest of the three measures when we have a negatively skewed distribution. Why is that? Because the mean is more influenced than the mode, and the median is more influenced by a few extremely low values. So here the mean, the arithmetic mean, in the case of a negatively skewed distribution is influenced or affected by a few extremely low values. Therefore, the arithmetic mean is not a good representative of the data in this case. So when we have a negatively skewed distribution, the mode is the largest of the three values, then next the median, and then the arithmetic mean. So the mean is the smallest, and so therefore It is smallest because it is influenced by a few extremely low values of the data. Therefore, it's not a good representative of the data. Okay, now we move to talk about measures of dispersion. Of course, in this topic, we're going to discuss four measures of dispersions, namely the spread, the range is one measure of dispersion, the simplest measure of dispersion. Then we move to the mean deviation. Then we move to the variance, and then we move to the square root of the variance, which is the standard deviation. These are the four measures of variation that we plan to discuss in this chapter. Now, first, let me discuss why measures of dispersions or reasons for studying measures of dispersion. Measure dispersions are important. Just depending on the measures of location, such as the mean or median or mode, is not enough. So you have to gain some knowledge about the measures of variation. Now, of course, as you can see, we have certain reasons for studying the measures of variations. First of all, a measure of location, of course, describes the center of the data. It does not tell us anything about, the spread of the data. Okay? Notice that a small value for a measure of dispersion indicates that the data are close together or clustered closely around, for instance, the mean. This implies that the mean, in this case, is very reliable. That is, it is a good representative of the data. When you have a small value for a measure of variation or a measure of dispersion. However, a large value for a measure of dispersion indicates that the data are very erratic, very variable, far away from the mean. Therefore, in this case, the mean is not reliable, is not considered a good representative of the data. Let me discuss, give an example why, having something about the variation of the data will, make your way easier and simpler. It's important. Let's say, for instance, you are going to cross a river. The information is that the average depth of the river, let's say, is 1.5 meters. Based on this average, perhaps you might not cross the river on foot. So you need more information about the variation of the depth. If, for instance, you were told that the highest depth is 1.6 meters and the lowest depth is 1.4 meters, then perhaps you will cross on foot because the average is 1.5 meters. 1.6 plus 1.4, you get 3 over 2, we get the average is 1.5. Great. So you need information about the measure of variation, about the variation, so that you can take your final decision about crossing the river on foot or not. However, if the information is as follows, they told you that the highest depth in this river is, let's say, 2.6 meters, and the lowest is 0.4 meters. Would you cross on foot? I don't think so. Why? Because you will have certain part of the river that has perhaps 2.6 meters. So having information about measures of variation is important. It can make your life much easier, okay, as we discuss in this example. Now, conversely, of course, as I said here, a second reason for studying the variation, measure the variation in a set of data. We first discussed the first reason. Now, the second reason for studying the variation of the data, the variation in a set of data, of course, is to compare the spread in two or more, distributions. To compare the spread, the variation in two or more distributions. Let me give an example. Of course, this is, as you can see here, we have, let's say, two factories, and these two factories are producing plastic chairs. We have factory X and factory Y. It looks that the average production, the average hourly production of plastic chairs in the two factories is the same, is 40 factories per hour. Production, 40 factories per hour. Here we're talking about production of plastic chairs. If the average hourly output of plastic chairs in the two factories is 40. Now, depending on the means of the hourly output in the two factories, you might think that the distribution of the hourly output in the two factories is identical. However, production for 8 hours in the two factories reveal that this conclusion is wrong. As you can see, the output in factory X ranges from 38 to 42. The data very close to the mean. However, the output in factory Y is very erratic, ranges from 30 to 50. So as you can see, the mean here is very representative of the data. However, the mean here is not representative of the data because it varies from 30 to 40 to 50. Here you have high, spread, high variation. The variation is very erratic over here. Here, the data are very close, are very, are very clustered around the mean, very close together. Over here, they are far apart, are away from each other. Therefore, the second reason for studying the dispersion is that you can compare, of course, the spread in two or more distributions. Okay, now we move to talk about measures of dispersion. I have already said that we have 4 measures of dispersions, 4 measures of dispersion or variation, namely the range, the mean deviation, the variance, and the standard deviation. Okay? As you can see, the range is the simplest measure of dispersion. It does not take into consideration all of the observation in the data. Okay? This is one of the defects of the range. It only focuses upon the highest value and the smallest value. So it is the difference between the highest value minus lowest value. This is the range. Okay? And as I said, the defect of it is that it only considers 2 values, the highest value and the lowest value. Therefore, this is one of the defects of the range and is the simplest measure of variation. Now, what is the second measure of variation? Of course, it is the mean deviation. Now, the mean deviation does take into consideration all of the observation in the data. So it is better than the range, because it does cover all of the data in the population, or all of the values. So this is the formula for the mean deviation. It is denoted by MD, mean deviation, which is the absolute value of x minus x bar, where x bar, of course, is the arithmetic mean of the values. Here it is stated for the sample, so it's going to be summation x minus x bar over n, okay, where n is the total number of observation in the sample. And as you can see, the two lines here indicates of course, the absolute value, okay? It is a known symbol to mean the absolute value. So here we take the absolute value of the, so you're going to have a non-zero value, because you take the absolute value of any negative number is a positive. Therefore, the mean deviation is going to be positive, okay? The third measure of variation is the variance, and the fourth one is the standard deviation. Here we're going to consider the variance for the population and for the sample. For the population and the sample. So let's first start with stating the formulas of the variance for the population. As you can see, the variance is non-negative, of course, and is zero only if all observations are the same. It's non-negative because also we take the square of the difference between x and the mean of the data in the population. Okay, so we're going to denote the population variance by sigma squared, which is a Greek letter, small Greek letter, which is called sigma. So sigma squared will be used to refer to the population variance, okay, which is equal to the summation of x minus mu, we square this one here, over n, where n is the total number of observation in the population. As you can see, x is the value of an observation in the population, where sigma, of course, is summation, stand for the summing of the values. Mu is the, of course, it stands for the mean of the, or the average, the arithmetic mean of the population, and n is the total number of observation in the population. Now we move to the standard deviation of the population standard deviation, which is the square root of course, the population variance, is denoted by sigma instead of sigma squared. Sigma squared is referred or is used to refer to the variance, where sigma, which is the square root of sigma squared, is used to refer to the standard deviation of the population, and is given by this. Okay, now the sample now, of course, the sample, the symbols here are changed. As far as the population variance, we use sigma squared. Now, as far as the sample is concerned, we use s squared to denote the sample variance. And to denote the sample standard deviation, we use s, which is the square root of s squared. Okay? And the only difference is that the symbols are different, and of course, the denominator of the variance of the sample is going to be n minus 1 instead of n. You're going to subtract 1 from the total number of observations in the sample. As you can see, this is the variance, which is s squared summation of x minus x bar, where x bar is used to denote the sample mean. As far as the population is concerned, we use the mu to denote the population mean. Now here in the sample, we use x bar to denote the sample mean. So this is of course, the sample variance. And then, of course, n is the total number of observation in the sample. Now, the sample standard deviation, of course, the sample standard deviation, as I said, is the square root of the sample variance and is given by this formula over here, which is the square root of summation x minus x bar, square over n minus 1. And, this sigma, which is the Greek letter capital sigma, is used to denote the summation, the adding up of all the data inside the summation.